Now, what I thought I would try and do is try and summarize the things I've learned about software that aren't really research. Because I came here when I was 18, and I thought I knew what programming was. And yeah, I knew a bit, but I knew a lot less than I thought I did. And I've learned a lot more, often in collaboration with people in this room over the years. So I'm going to try and do roughly the following. I'm going to claim that software is fundamentally about dealing with incomplete, often half-baked, and ever-evolving specifications. That the path to creating software inevitably involves friction, and that adding new features to software is much easier than improving its flaws. In order to do this, I'm afraid I'm going to have to take some familiar terms and concepts and look at them a little differently than we're used to. And there is some good news, I hope. Once I've done that, that's right, the text will be coming. I admire the optimism that will start now. Once I've done that, we can look at software in a new light. And don't worry, it's 2025. I promise I will at least briefly mention AI. So, let's start with a question which virtually no one asks out loud after the first week of a first-year undergraduate programming course. What is a program? Is this a program, ladies and gentlemen? You have to say something. Yes, I've got a yes. Actually, I was expecting a no, especially from... yeah, I think it's a program. Now, I think that most of you, if I asked you, would say, well, I'm going to define a program. I think it would be something along the lines of, it's a sequence of instructions a computer can execute to perform a task. Now, this screenshot clearly satisfies that definition. I no longer think that definition is adequate. Instead, I now think of programs as a form of specification. Let's define a specification as follows. It describes my desired outcome, doesn't have to describe every single step needed to achieve that outcome. So, imagine you are brave or foolhardy, and you run a software company. I run a software company, and you decide to hire me. You want me to make software to track all the widgets your company makes as they move through your factories. You've given me a high-level specification, track widgets, and my job is to create a program that can make this a reality. So we can thus say a program is a specification that contains enough detail for a computer to make the desired outcome occur. Notice that I have carefully avoided saying anything about a sequence of instructions. Indeed, as we now know is plausible, some programming can be done with high-level, vague English. So that's the first mention of AI. What's programming? Well, if a program is a specification, then programming is the act of turning high-level specifications into lower-level specifications. That's trickier than it sounds. Returning to our original example, the high-level specification, track widgets, is pretty vague. That's not just because the hypothetical boss of the factory is lazy, maybe he or she is, but because they can't possibly know every detail of a large organization. They won't know all the points in a production line where widgets could be tracked. They probably don't even know all the widgets that they make anymore. However, if I want to make software that, and this is the bit I care most about, useful enough for me to be paid, I either have to know all those details or be willing to put as much effort in as necessary to understand them. So then we need to ask the next question. What's a program? A programmer is someone, and we'll stick with someone, not something at the moment, who translates high-level specifications in a problem domain, widgets in a factory, that sort of thing, into low-level specifications. At the moment, we would think into a programming language. In other words, a programmer nearly always has to be expert in two domains. Now, that was not something that occurred to me when I started here. So we've now set up two obvious challenges with our definitions. How do programmers know what details in a specification to add, and how can they be expert in two things? I mean, I've been trying to be expert in one thing, and it's been not entirely successful, but we'll come back to both of those shortly. But before that, let's ask, what's software? So we agreed that this is a program, right? I mean, one person said that. That person spoke for all of you. I don't think most of us would say this is software, right? I think we'd say no. Because implicitly, our definition of software is lots of programs working together harmoniously. So an operating system kernel is a program, but together with its various utilities, it hopefully constitutes software and not merely programs. So in that sense, software implies both the design and implementation of a set of programs. So I want to emphasize that sense of harmony, because I think that's what is crucial here, and it's why I've come over time to care more about software than programs. Okay, so good news. That's the end of the redefinitions. You now know the slides work. So my claim is that these definitions aren't just me being pedantic, but they give us the tools we need to understand a triad of factors that I've come to think help us understand the true nature of software. So number one, software occupies a liminal state. I know it's a weird word. I chose the example of a factory making widgets deliberately. Factories are part of the real world. We can see them, we can touch them, we know they're subject to all sorts of constraints such as gravity. But specifications occupy a dream world. We can specify whatever we want, even if it cannot be made reality. So I can specify that each of you should give me £50 as a result of this talk. But I don't have the army necessary to make that happen. Software thus occupies this liminal state between the real world of factories and the dream world of specifications. Hardware imposes some constraints on us, computers have finite memory and so on, but those are rarely particularly onerous. So programmers thus find themselves in this really big problem. They have these input specifications that have many degrees of freedom. So many degrees of freedom that if maximally implemented, we'd never finish and the software would be horrible to use. So we thus have to place constraints on software to make our job tractable and the software usable. A vital part of programming, therefore, is to try and work out what the best soft constraints are. For example, I might decide that widgets can only be in one factory at a time. Fortunately, I know my hypothetical company doesn't manufacture quantum devices or employ quantum cats. But soft constraints aren't generally that clear-cut. I might decide that I only need to track widgets when they enter or exit factories, but the company might later realize that they also need to track widgets between factories during transport to understand defects that occur there. The challenge with soft constraints is that they are hard to quantify or relate to the real world. When programming, I frequently find myself presented with a fork in the road and no obvious way of deciding which is the right one. Sometimes a bike ride helps, but not always. Reasonable people struggle to articulate why a particular soft constraint should or shouldn't be present, because so much of what we are thinking about resides in the dream world. Even worse, getting a seemingly innocuous soft constraint wrong, especially if it happens early in a software's lifetime, can ruin the eventual usefulness of that software. 2, the search for specification problem. So I said earlier that high-level specifications are vague. They aren't vague just because we're lazy and stupid, but because we can't know in advance everything that the resulting software should do. The only way to find out what the software should do is to build the software. In some cases, we're simply filling in missing details from the original specification, but surprisingly often, we discover that the specification is inconsistent internally or at odds with the real world. Whatever the reason, as we create a program, our idea of what the high-level and low-level specification should be keeps changing. This has a profound effect on programming. It means that iteration is necessarily a part of virtually all software development. Only in the most tiny or tightly specified domains, maybe a nuclear plant, if the fish disco thing ever lets us build it, can we possibly know everything we should do in detail up front. For everything else, we should expect that we have to repeatedly revise our understanding of what we want, what we've got so far, and how to get from here to there. It also implies that programmer and client, or even two programmers, cannot be expected to have the same idea of what the software should look like in the future, or how best to get there. That means the miscommunication is built into software development. So can we do anything about this? Well, we've tried repeatedly So formal specifications help in some cases, but in general, creating a complete formal specification is strictly more effort than creating the equivalent program. Software modeling, UML and the like, worked okay for high-level programs, but they failed. I failed when trying to apply it to low-level detail. Maybe the best success we've had is when we've been able to capture a family of problems in domain-specific languages. But that only works for simple, well-understood problems. So I won't go into this one, the observer effect, in quite as much detail because the idea is fairly simple. Users always end up using or wanting to use software in a way that its designers did not anticipate. Sometimes this opens up new opportunities, and sometimes it uncovers horrible flaws. There are two important differences between this and the circular specification problem. The circular specification problem is noticed by programmers and rears its head early in the development lifecycle. The observer effect is noticed by users and happens much later in time. Fundamentally, most organizations don't know how to let users try and complete software, and users struggle to give us feedback we can understand and take action on. There has been some progress recently. Generative AI gives us a way of sketching out some aspects of software at low cost. You can mock up a user interface relatively cheap. That's pretty useful, and I think it will keep progressing, but there seems to be a limit to how far sketches of the future can take us. So, as I went through this triad, I explained some of the individual challenges they give rise to. But basic common sense tells you that triad doesn't describe all of the challenges we encounter when creating software. So my claim is that the unifying concept we're looking for is friction. The original definition from Clausewitz is, to my mind, genuinely profound. But more recently, programmers have, as is our one, we've rediscovered this without realizing it, reinvented it, and found a much easier way of expressing it. Basically sums up my entire career. I'm still stuck on the same problems that I started in about 2003. So we always think we are the clever ones who can sidestep the circular specification problem et al. But every second of my adult lifetime computing has convinced me that this is not so. Everything ends up being harder than I expected to be, for reasons mostly I couldn't anticipate. Friction is thus as real a thing in software development as it is in military affairs. A great deal of hope in computing has gone into trying to remove friction as a concept. But even 200 years ago, Clausewitz realized that this cannot be done without trade-offs. So friction is not some temporary annoyance or temporary flaw. Trying to remove it imposes unsustainable costs. That's not to say that we can't reduce friction in software somewhat, because there is some skill in programming, I hope. But when people claim their solution reduces friction to zero, I think we should be very skeptical. So, no one's argued with me, so that means you agree, obviously, that the triad is inevitable, friction is inevitable, and I hope to convince you of one further consequence. Again, I'm going to pinch a concept from Clausewitz and say that software regularly reaches a culminating point. So over time, the friction inherent in creating and maintaining software increases until the costs it imposes outweigh the benefits we're able to accrue. The software has reached, at that point, a culminating point. So if you try and push too far beyond that culminating point, the quality of the software rapidly degrades. That quality is both internal and external. So if you've upgraded your software on something and it's gone wrong, the internal quality has exceeded the culminating point. If you've upgraded your software and it's now more difficult to use, the external quality has exceeded the culminating point. What interests me about this is that it need not be permanent. If one addresses enough of the causes that cause the software to culminate, the software is once again ready to have new features added. What needs addressing and how it's addressed, of course, vary. For example, refactoring is a term most of us recognize, I suspect. It means that we try and reorganize a program's internals to make the program easier to work on. We can also do various things to try and delay or put off the culminating point. So perhaps the biggest change in software development in my professional, whatever that word means here, lifetime has been our attitude to testing. So we now expect nearly any good program to have a large, fairly comprehensive test suite. Creating a test suite makes it less likely that we introduce bugs when we're adding new features, but to my mind, its major use is for regression purposes. It allows us to change a program with much greater confidence that we're not undermining the quality of the existing functionality. So the concept of a culminating point has led me recently to what I think is a surprising conclusion. You can throw tomatoes at me later. Traditionally in software, we have venerated new features. Marketing of a new version of software invariably focuses on all the new things it can do. People in industry are almost exclusively promoted on the new features they deliver. Even the software curriculums at universities implicitly assume that students will be making new software or adding new features in the future. One would therefore surely think that the hardest thing in software is to implement new features, and I assumed that for many years. I now think I was completely and utterly wrong. When software is some way from its culminating point, adding new features is often trivial. So I can sometimes implement multiple new features in a single day in congenial software. In contrast, when software is at or even near to its culminating point, I sometimes will have to spend days understanding and rejigging the internals just to get back to the point where I can make some sort of progress again. So there's a lesson and a challenge that I've derived from this. First, the lesson. So we, and I'm using the we as the software community, should recognize that our best techniques, our best tools, and that, yes, our best people, should be put to pushing back the culminating point as far as is possible. Doing so makes adding new features easy. So put bluntly, it would be better to let the intern implement the new features. Second, the challenge. How can we recognize when a program is nearing its culminating point? Right now, honestly, I don't know that we can do much better than I know it when we see it. And I doubt there'll ever be hard metrics to help us here, but maybe we can define some sort of rules or thumbs or analyses that could help. Seems to me a fruitful area of research. I hope some of the better minds here than mine will put themselves to working on that in the future. So most of the things I've described in this talk can be applied to other areas of life than software. Some parts of software seem a little like architecture or mathematics or politics or the military, or you get the idea. What makes software interesting isn't each constituent thing in isolation, but how they come together. You'll notice, and those of you who have the dubious pleasure of knowing me well might be surprised that I haven't talked about concrete technologies. I haven't talked about my favorite programming language, my favorite operating system, my favorite editor, or anything like that. And that's because these things are, and I say this as someone who's devoted far too much of his adult life to this stuff, ephemera. They make a difference, of course, but they're not fundamental. This then leads to an obvious question. Are the challenges I've outlined for software just a consequence of our current immature technologies and techniques? Or, and I'm sure this is the question that I'm going to be asked about 10 times more before the year ends, isn't AI going to put programmers out of jobs? So AI has had, obviously, a small but meaningful impact on programming already. And it's possible to imagine a far greater impact occurring, though maybe not quite as soon as is sometimes stated. It's certainly possible that it will ultimately sweep away all our existing programming languages, operating systems, but those are, as I said, ephemera. What I hope I've shown you here is something maybe more fundamental. That software isn't a puzzle that has a definite solution. It is a set of challenges that, annoyingly, adapt themselves to our ambitions. Automation can help reduce the effects of, but it can't fully remove those challenges. For example, the circular specification problem will, I believe, always remain, though maybe one day we will be able to produce the next iteration of software a bit more quickly. That said, it is worth thinking about how all this stuff will affect us as humans. My current best guess is that humans will still be doing quite a lot of programming, at least if you accept my definition of programming as involving specifications. However, it may be that fewer humans have to be actively involved in programming. Specifically, these days, I divide programmers, in my mind, into three kinds, with thanks to Doug Lee, who helped with some of this terminology. The first two categories of programmer here vary in which side of the programmer duality their expertise lies. Put simply, technologists, and I flatter myself that I might be one, are experts in things like programming languages. Operators are experts in things like tracking widgets or biochemistry or accountancy. Enthusiasts, different thing again, I won't talk about them in detail today. I think that those technologists willing to adapt will be programming in some shape or form for some time to come. For novel software, their experience, their intuitions seem likely to be necessary to lessen challenges like the circular specification problem. In contrast, operators, for whom programming is generally a cost they have to bear in pursuit of a task they care rather more about, are from a programming perspective mostly working on less novel things. I expect them to benefit much more from automation and much sooner. However, it's hard to know for sure what will happen. The history of our subject is that our ambitions for software rise to whatever our current technologies and techniques allow us to produce. One of my favorite quotes is from Greg LeMond, the Tour de France winner. He said, "It never gets easier, you just get faster." No matter how much automation we develop, I think the fundamental nature and challenges of software will remain the same. AI can't suddenly make software inhabit a non-liminal state. We will still unknowingly provide incomplete, incoherent specifications and so on. Now that might sound like a downbeat note on which to end, but I see things very differently. Most of us in this room have stumbled into a field whose challenges are likely to continue to rise in direct proportion to our abilities. The specifics of those challenges might change. I hope they keep changing, but I don't think they're going to suddenly disappear. Indeed, I think there's a huge amount of interesting work for us to look forward to. I've been genuinely lucky, blessed to work with many people in this room in the past, and I hope to continue doing so in the future. Because, frankly, computers have humbled me many times, but working with really good people has rarely been short of inspiring. After all, you've not only been willing to put up with my sense of humor, but you've sat through this talk without complaining and hardly anyone going to sleep. Thank you very much for listening.